Perfetto.
Okay, so I think we can start.
So we have now the third lecture of Professor Francesco Pederiva. So please, you can start.
Thank you, Ignazio. So, contrary to what I promised, I decided that I needed to say a couple more things to complete what we said Friday, because otherwise it's difficult to understand why what I explained is useful for an actual calculation or an actual application. So let me, first of all, I hope that you were able to solve the simple game that I gave you on Friday, and essentially the solution of the game is that the probability to win the game is cos square of pi over 8 for each of the cases that you might have. So cos square of pi over 8 is about 0.853, something like that. And this means that the possibility of sharing an entangled Bell pair for the two contenders actually improves the probability of winning with respect to the classical standard case. And this is not obvious. This is not obvious. And of course, I mean, you might say, well, how do I choose these angles? It's simple in some sense because you could parameterize the probabilities that you find for the various states or for the various coefficients you want of the expansion on the computational basis, and at that point, in principle, you could just perform a very quick optimization to find the correct value. But I mean, you can easily convince yourself that you take a value different from pi 8, you will get a worse, in general, probability of winning the game. If for any reason there was some difficulty, we can discuss this tomorrow afternoon in the Q&A session. Okay, instead, today I want to show you another example, and it's another elementary circuit, quantum circuit. It's the one that provides the so-called phase estimation. So, what is this about? So, in general, you have a system that you want to study. For example, this is described by some Hamiltonian, and you would like to have some information about the spectrum of this Hamiltonian. So you wonder if it is possible by means of a quantum computer to be able to extract, for instance, the eigenvalue corresponding to a certain eigenvector, or say to some approximation of an eigenvector. So for the moment, let us suppose that we have some mechanism that provides us with a certain state psi, which can be defined for an arbitrarily large Hilbert space. So I mean, for arbitrarily complicated interacting system, if you want. And the idea is that we want to know what the corresponding eigenvalue is. So finding an eigenstate is not a trivial task in general. And there are many algorithms that are on the market that pretend that they are able to do that. Some even work, let's say, or at least have been demonstrated to work for some relatively simple case, but in general, it is possible to find solutions for this problem. The problem possibly might be the efficiency of such algorithms, so how they scale with the dimensionality of the system and similar things. But let's assume that we have that. But you have only a quantum computer. Now you need to compute the corresponding energy. So this can be done by constructing an interesting circuit. Here we put on a single wire here the state psi. So you have to interpret this as actually possibly a multi-qubit state. This could be described in terms of 8, 10, 20 qubits, doesn't matter in some sense. And what we try to do is to see if we can get information by coupling this system to an external degree of freedom. So we actually expand the Hilbert space, and we hope that by expanding the Hilbert space, we can somehow simplify the problem of calculating this eigenvalue. So the algorithm goes like that. We take this. This is a single qubit. Okay, this is possibly a multi-qubit state. This one is just a single qubit. We don't need a large Hilbert space here for the coupling. First, you take this qubit that is prepared. It's prepared in the state 0 to begin with. You apply an Hadamard gate, and we saw what an Hadamard gate does, and then we use this extra qubit to control a certain operation that I will define now. Let me just write this as a CU. It's a bit redundant as a notation. Then we put another Hadamard. And we perform a measurement on this extra qubit, okay? And we leave this alone. What is this transformation down here? Well, this transformation down here, which I call U, okay, is essentially E to the I H T. So this is a propagation of the state that describes the whole quantum system by a certain time t. This is definitely a unitary transformation, so this is something that we can implement on a quantum computer. Again, you might wonder how complicated it might be to implement such transformation if I have an arbitrary h, and I will tell you in a moment, once we end discussing this simple algorithm about a theorem that actually guarantees that whatever is the dimensionality in principle of the system, it is possible to find arbitrarily correct approximations to this unitary transformation with a number of gates that let's say grows decently with the level of the approximation required. So this is a task that that is not impossible. We'll discuss about this in a moment more in detail, and this is what in some sense I wanted to introduce, but I want to introduce this in the context of some practical application, let's say. So we said last time that one way in which you can implement a controlled operation is that of writing essentially the operator in a matrix form with an identity here, and whatever is the matrix that describes the operation U, the operator U, down here in this corner. So if you want to perform this phase estimation on a system, for a system that can be mapped onto a single qubit, this would be again a 2x2 matrix. But if you want to extend this or to use this for a general, I mean, some arbitrary system, this could be a 2 to the n by 2 to the n matrix according to the need. Well, we can say that here we have a parameter t. We can consider this t as a parameter of this unitary transformation. Okay. Now let's see what this simple circuit does. Again, let's say by the way, when I couple a system to a qubit like that, this qubit is usually called, this is a jargon, an ancilla qubit, that I realize right now that on March 8th, this is not going to be very nice in some sense, but sorry about that, it's not my fault. It's called ancilla qubit because essentially it's a qubit that serves in some sense as a support for the calculation. It's not part of the system that you want to study. It's something that you add in the game. So let's take the ancilla and let's operate with the Hadamard, and of course this 0 is transformed into 1 over square root of 2 0 plus 1. We can also put an A here just to remember that these are ancilla states. Okay, now we can turn to the whole system, and we can operate essentially with the controlled U, the controlled propagator, according to the state of the ancilla. Oh, remember that psi is an exact eigenstate, or it's a reasonable approximation of an eigenstate. So essentially we can assume safely that the propagator applied to psi is simply e to the I e t times psi. Remember that here we are in a context in which all these operations are not obvious, because the temptation, I mean, when I say that this is an algorithm that can be applied on a quantum computer if you have a state here that has been prepared. Remember that in principle, you might have a simple way to compute this energy, which is, okay, let's read out the coefficients of the wave function, and then we'll also say something about that in a minute. And then let's compute the expectation of the Hamiltonian, for instance, on a classical machine or something like that. I mean, remember that so far the name of the game here is not to demonstrate that these are absolutely efficient algorithms, but it's just to demonstrate the concept of performing computations of this kind of on this kind of systems. So before you start asking yourself, what is all this about? I mean, I just want to warn you that this is what you're looking at, not something that tomorrow you can use to do the calculations that that you're planning to do for your research in some sense. Okay, this will come in the future, but so at the beginning, the state is described as this tensor product, and this, after the application of the control rotation, goes into something which is 1 over square root of 2, 0a tensor psi, because if the state of the ancilla is 0, we do nothing on the state of the system. While if the ancilla is in state 1, we propagate by a time t. So we apply the propagator for a time t to the state of the system, and this ends up, since as we said, the psi is an eigenstate in adding a phase essentially to this term. That's why we're calling this algorithm a phase estimation. Now we go and apply the second Hadamard gate, and the second Hadamard gate brings this state into, let me, oops, too many, into essentially 1/2. Then I have all the various combinations that arise from and let me just give you one. Well, we can do that. The first, we can do that explicitly. Doesn't hurt. The first term actually generates 2 terms, since the Hadamard. I already collected the 1 over square root of 2 outside, which will appear everywhere. So the first term gives me these 2 terms here, and then I have e to the I e t. Here I'm rotating the 1 state, so this gives me 0 minus 1 after the Hadamard times psi. So this again is 1/2 0a tensor psi plus 1a tensor psi plus e to the I e t 0a tensor psi minus e to the e I t 1a tensor psi. And we can collect the coefficients of the 0 a vector tensor psi and the 1a tensor psi, the x. So we have something like 1 plus e t 0 a tensor psi plus 1 minus e to the I e t 1 a tensor psi. Okay, so this is the typical kind of calculations that you perform to set up a quantum algorithm. And at this point, we said that we are going to measure the ancilla. It looks strange that in order to find something that has to do with the system, which is described by the state psi, you have to go and measure this extra degree of freedom, this extra qubit that we are adding. We make to interact in some way with the system. In that, somehow you have also the convenience of this method, because yes, you have to apply one operation, one propagation to the system, but then you don't need to measure the whole system, which in some sense is you can imagine is an operation that is safer in terms of the accuracy that you can obtain. Obviously, this one here, everything here is has to be interpreted. Well, these are numbers in this case. Okay, so complex numbers. And so these are the coefficients in order to get the probability. So the probability of measuring the zero state for the ancilla is simply the square modulus of the coefficient, which at this point becomes well, there's also 1/2 in front, of course, so that becomes a 1/4 here. Not to forget about that. And this is the square of the real part, and the square of the real part is 1 plus the cosine of E t square plus the square of the imaginary part, which is simply sine square of Et. Okay, which is, if we expand the square, this is 1/4 1 plus cos square Et plus twice the cosine of Et plus the sine square of Et, and at the end of the day, we get 1/4 times 2 plus 2 cos et, and so 1/2 1 plus cos et. Okay, so this is the probability to measure the ancilla in the state 0. What is the probability of measuring the ancilla in the state 1? I'm not going to redo the calculation because it's trivial, of course. But let me just erase to make space. The result is analogous. The probability of finding the system in state 1 at this point is 1/2 1 minus the cosine of et. So, what do I do now? So, first of all, what does it mean? What does it mean that I'm applying this measurement? So, how can I get this information? What experimentally, let's say, or from the computer? Because if I go back here and I look at the circuit, essentially, if I prepare the system in this state initial, which is 0 tensor psi, and I run the circuit, well, once I go to the measurement here, and I apply this measurement, what I will read is either 0 or 1. By itself, this single measurement doesn't tell me anything, absolutely anything about the probability, because this is just a single measurement, okay? So, in some sense, what I need to do if I want to get some information is to sample these probabilities, which means what? Which means that I have to repeat this procedure a large number of times. So, if I want to read out the probability of the ancilla to be in state 0 or in state 1, because this is what I want to do. So I have psi, I know nothing about the eigenvalue E in principle. I set up this circuit, and from this circuit, I want to get the value of E, okay? And I get the value of E if I'm able to measure the probability. Notice that I don't need here, in order to have something that depends on E. No, I don't need to have access to the coefficients, so to the amplitudes. I just need access to the probability. And this is simple because I run this experiment once, I get either 0 or 1 here. I run twice, I get either 0, 1, and blah, blah, blah. I do this 1,000 times, 2,000 times, 10,000 times. This, of course, influences the accuracy by which I can derive my results, and of course there is a statistical error associated to all this, but eventually I can measure this P1 and P0. If I go, typically if you use one of these commercial systems, And you could in principle just take, as you will see Wednesday in the practical session, in machines like the machine from IBM or so, you have a graphical interface, provided that you can set up this UART. You can try, you could try this simple circuit with an Hamiltonian, which is like, I don't know, sigma z. So I don't know, you're pairing the spin of a fermion to an external magnetic field. So you have an Hamiltonian, which is simply something like B sigma z or something like that, okay? And of course, there is, all the results are trivial, and there is no need of a quantum computation, but you can just try out and see that this works in some sense. And yes, you can adapt, or you could try something also with two spins and some coupling term or whatever, very simply. So something for which you know the eigenstate, so you can start without doing anything else from a solution in such a way that you know that whatever you get should be correct, unless you do some mistake, just for the sake of testing. And actually, you prepare your system, you run, and for instance, the IBM machine provides you with the possibility of repeating automatically. You just say, there is a little menu that you can open, and in this menu you decide whether you repeat your experiment 1,000, 2,000, up to 8,000, if I remember well, times. So that you get an estimate of how many times, or not an estimate, no, what you get is the number of times in which you measure 0 and the number of times in which you measure 1 here for your oscillator. And graphically, you would get something like this. You have state 0, you have state 1, and they show you like a kind of an histogram that for a single qubit would be just given by 2 bars. If you have of course a larger computational basis, you will have more states, and for each one of the states, essentially the quantum computer gives you back exactly this probability, which is simply the number of times you measure either one or the other divided the total number of attempts. You might wonder what's behind that, and this is a perfectly legitimate question, in the sense that if you just go and put the hands in the jam a little bit, you realize that deciding whether a machine like this is in state 0 or in state 1 when we take the measurement might by itself not be a completely trivial task. Plus, as we will see today, I guess later, there are some issues related to the fact that the machine is not perfect. So usually you should interpret these objects like having some error bar here, these histograms, because this readout is dependent on a number of things, including the current state of the machine. In fact, if you repeat the same experiment twice at a distance of a few hours or a day or so, you're very likely to get completely different results. But say, I mean, one might have a way to estimate the uncertainty that you get from this kind of measurements. Of course, cumulating some statistics. So the point here is that what you get is not a number. What you get in general is the sampling of some probability distribution, which is given by the amplitudes in the end that you have on the states of the computational basis, and that all these numbers have to be treated as coming from a sampling. So you have to apply all the data analysis that you would usually apply in a calculations like a Monte Carlo estimate of some kind. In the end of the day, you might regard this as a way of sampling the probabilities of finding the system in one of the states of the computational basis, and so it's like a sort of Monte Carlo estimate of the state in which your machine is found at the end of the calculation. In this case, we don't measure all the machine, we just measure one qubit, the oscillator qubit. So this is a very important concept. This is the kind of results that you can find with a quantum computer. It's a bit disappointing in a way, because you would expect getting numbers or print out some numbers as you would print out them in a computer. Well, you get numbers, of course. I mean, you get something like I don't know, 0.431, 0. In this case, okay, now I did 569. Is that correct? Yes, probably. For a single reading, but of course the next, if you redo the calculation, you could well find something like 0. I don't know, 398, and here you could find something like 0. Whatever 602, something like that. Okay. And if you repeat the measurement again, you will get yet another number, and blah blah blah. So this is the kind of results. But you know, there is a way to translate these results into something useful, as long as you can perform some statistical analysis. But it's not trivial. Once you have these probabilities, and you did all you could in order to establish within a certain statistical error, a certain uncertainty, a certain uncertainty is nice. These probabilities, then you can compute the energy at the end of the day. This is what, so because if I take P of 0 minus P of 1, in this case, for instance, what I get is twice, no, nothing, no twice, no 2 cos ET. So T is a parameter that I fixed. So T is a number that I know. And so just inverting the cosine, I have an estimate for E. Of course, there is an ambiguity of an angle pi, but that has to be, I mean, there are ways in which one can, of course, combine these results with others to get rid of this phase ambiguity in some way. But in general, you see the difference of these two probabilities gives you back the physical quantity that that you want to estimate. Okay, so this would give you back the sort of eigenvalue. So this is the phase estimation algorithm. Okay, so all this is very simple, just on the board, and you might wonder, okay, there are of course many questions that are probably come into your mind right away. So first, but are you really able to prepare the state psi, which is a legitimate question, and said something about this. I mean, there are algorithms that are set up to prepare the machine in a certain state, which is typically an eigenstate of some Hamiltonian. This is particularly useful, for instance, if you have an algorithm that can prepare the machine in the ground state of some Hamiltonian. An algorithm like that would be, for instance, an algorithm that propagates in imaginary time, which you understand immediately that is not a simple task, because the imaginary time propagator is not a unitary operator, so it cannot be implemented naturally on a quantum machine. You need to play other games, and one of my students is, for instance, is particularly expert in playing this kind of games and being able to extract ground states for in principle generic Hamiltonians. The second is, okay, you write this gate as a single square, something very simple, but what about implementing this this unitary transformation? I mean, in general, implementing a generic transformation might be very difficult. Again, say it's possible to proceed to some kind of compilation of this, which can be regarded as an instruction. Compilation means that you try to reduce. Reduce is not the correct word. To expand, it's better. In some sense, this operation in terms of some gates that you have available. Quantum machines, in general, provide you with a finite number of operations, which will be a few rotations, maybe parameterized rotations, in some case, a C-naught. C-naught is the typical entangling gate, and okay, so you have this bunch of gates, and as the ones that I described last time, and with those you have to reconstruct somehow a generic transformation. It's not absolutely obvious that this is possible, and the second problem is that even if it is possible, this might in principle cost you the use of an exponential number of gates, which is something you don't want, again, because. So let me give you very quickly. I wanted to squeeze this part in the last class, but I decided that we could go a little slower. And I will not do all what I wanted to do here, but just point you to a reference. So I give you the reference first. It's found on the archives. So and you can give it a look. I think it's a very nice paper that discusses this problem of being able of expanding arbitrary unitary transformations in terms of elementary gates. So this 0505, 03, 0, version 2, okay? And this is a paper by Christopher Dawson. and Michael Nielsen. And the title is the Solovay. So this is Solovay-Kitaev. Algorithm. And what we find in this paper is a nice discussion of what is the so-called Solovay-Kitaev theorem, which is a very important very important theorem that sort of it's at the basis of the fact that I think in recent years people have started looking at quantum computing in a more optimistic way. And let me just give you a definition and then the statement of the theorem, and then we'll comment very briefly. So the definition is that of an instruction set. And essentially an instruction set, G, let's call it cal G, for this is for a d-dimensional qubit. What is a qubit? I mean, when you consider a bunch of qubits, no one prevents you from thinking of your system as described by a single object that has many states. So in some sense, it's if you have a system that has 4 states available, so instead of having just a state 0 and a state 1, you have a state 0, a state 1, a state 2, and a state 3. No one prevents you from imagining that this is a system that is described by the product of 2 qubits, even if physically this is just a single system with 4 levels. So a system with d levels is called a qubit. Okay, just an extension of the concept of bit, but it doesn't. I mean, for our purposes, it's not. It doesn't add much to the fact that you can describe a system with a certain number of qubits. Just take it. So. The G is an instruction set. If G is a set of G is a set of gates, such that all gates G in this set are essentially operations in SUD. Okay, so they must be unitary and have determinant 1. For each gate, the inverse of the gate belongs to G. So each gate must have the inverse. And 3, G is a universal set for SUD. What does it mean, universal set? It means essentially that if you take any U in SUD, okay, and you take any small number epsilon, you have a product of a certain number of gates, okay, such that this is let's call this S, okay, such that the distance, the operatorial distance between S and U is less than epsilon. Okay, so essentially this means that you also say that this set of gates is dense inside the SUD. You understand what the concept is here, okay? You have potentially a small set of instructions, and by these instructions, you want to reconstruct any unitary transformation in SUD D, okay? I'm not talking about SU2, I'm talking about SUD here. So this is very general, a general definition. And the idea is that first, you can have sets such that this reconstruction, this approximation is possible, and it's possible with arbitrary accuracy. In some way, you must have a sort of, with many quotations around, a sort of ergodic property of these gates, of the transformation built on these gates in SUD. Okay, so these instruction sets exist, and proving that they exist. Proving that they exist is outside, let's say, what we can do right now. It gets a bit complicated, but we can definitely find out sets that are very limited. We're talking about 6, 7, 8 gates possibly that constitute this kind of universal sets. Let me just to make clear what this kind of measurement might be. Of measure, sorry, in the operatorial space. So typically this distance, you take all the states in the Hilbert space, and you take the action of the difference of the two operators on the state. So this must mean all normalized, of course. And just you take just the upper limit of this difference. And this defines the distance between two operators. By the way, you could imagine that this measure, as many other measures, I mean, there are many ways in which you can measure distances in the operatorial space. This could be a definition of what you call the fidelity of S that reconstructs U. So usually the fidelity is normalized in such a way that the fidelity is 1 when S is exactly equal to U. So when essentially it exactly reproduces the operator you want, and it's 1 minus this distance normalized if S does not coincide with U. Okay, so there are other ways in which you can define the fidelity, actually, which is always given in relative terms. So fidelity of 100% is the fact that this describes the fact that S is exactly U, say, and then you go down, and this means that you end further and further away from the target operation. Okay, the theorem, the Soloway Kitaya theorem. Let me find the correct words written here. And I'm not going beyond what I'm saying now, because, as I say, if what you find is this very nice you can find in this paper that I quoted a very intuitive way of understanding this theorem. But this theorem says that if, so, or given G, which is an instruction set, in SUD, and given an accuracy epsilon, of course, it has to be greater than 0. There is a constant C, such that for any U in SUD, there is a sequence S of gates belonging to G. And this is the important part of length. And this is the real deal here. Log to the C of 1 over epsilon. Such that, again, the distance between U and S is less than epsilon. So, where is the big deal of this theorem? The big deal of this theorem is here. So, this tells us that if we want to approximate a certain unitary transformation, let's assume that we have some time evolution for a state psi. So we start from a state psi here, and we apply a unitary evolution, which might be, we have time on this direction, let's say, and we are applying a U, an operator U, a unitary U, which is parameterized with time. This could be, for example, a useful one, e to the I ht. We will see tomorrow that e to the I ht is what allows us to study, for instance, nuclear reactions in a direct way, in principle. If H is a nuclear Hamiltonian, and I know how to perform this operation, I can actually just simulate a reactor in this machine, because contrary to what you typically do for studying scattering, here you directly follow the time evolution of the system, which is something that you usually don't do. But to come back to us here, the point is that we don't know how to implement U directly, or better, this is not what we want to do. What we want to do is to use an S, okay, which is an S of, you can call it S of t again if you want. That will actually give us a kind of approximate evolution, and that essentially if you want, ends up in a state which is not exactly ut applied to psi, which is the one that we would like to have. But this is rather an S of t, which is applied to psi, which is arbitrarily close to this ut to psi. And the point is that this evolution is not a continuous evolution as it is implemented on the quantum machine. If you want, we can picture out our evolution as a sequence of digitalized evolution. So each one of these points is like the evolution that is given by one of these gates in the sequence. And say, now I exaggerated this, of course, should start closer to the other one, but just to have a kind of a pictorial view of what's going on. You have a digital representation. Well, actually, the red one is not digital. The red one is the exact one. Sorry, the red one is the exact one. So forget about the dots, okay? Because that is what it is. This is the one we want. We want to reproduce this unitary in terms of the sequence of gates. And of course, if I want to get closer and closer in this chain, I have to add more and more gates. But the number that I have to add, if I want to get closer and closer to the distance epsilon, remember that this distance is defined in terms of this distance in some way. The number grows like the logarithm to the power c of 1 over epsilon. Okay, this could be much worse than that. It could be this is less than linear in the long term. So this is extremely is an extremely good result. It tells you that approximating arbitrary unitaries is not something that is going to cost you, not even as a power of the accuracy, or and even less exponentially with the accuracy. Okay, it costs you logarithmically, which is a very good news in that sense. By the way, in this paper, you can prove it. I mean, it's proven explicitly, and it's nice. This is what I wanted to do, but it takes too much time. You see that for SU2, you can prove that the length of the chain goes like the logarithm to the 3.97. This is quite funny. 1 over epsilon. And you can also prove that, and this is even more interesting, that the time it takes to evaluate the chain, because the problem is that then I have to find this sequence, but the time it takes to find this sequence actually grows even less than the number of gates you need, which is funny in a way, because you need more and more gates, but the time it takes to evaluate or to find this sequence of gates grows slower than the number of gates itself. And I invite you to look at this paper because it gives you a sense of what's going on in these terms. That and it's again, I think, one of for me it was quite surprising, this result, when I heard of it the first time. And actually it's I think it's very interesting. So the point here is that we have very good news in the sense that it looks like everything is feasible in a way. Of course, there are other ghosts we have to fight against. So there are not just good news, there are also bad news. So I would say this is the good part. The bad news, which at the moment are kind of prevalent on the on the good news in some sense. Are that the systems are not perfect. So, of course, when you do all this, I mean, you follow all these arguments, you're assuming that essentially your qubits and your gates actually perform ideally. So there are no errors, there are no there is no dissipation, no decay. We will just discuss this in a second. So when I told you that, for instance, you get results of this kind, and I said, well, you could depends. What you get actually depends on how the planets are aligned at that particular day and time of the day. Well, it's this is a problem that raises from also from the fact that these machines are not ideal. I mean, if the machines were ideal, there would be no reason in principle to measure uncertainties that are above, say, the statistical estimates. But the problem here, and maybe this wasn't clear, is that these fluctuations that you get might not just due to the fact that you have a statistical estimate of these probabilities, so that you have a finite number of samples, let's say. There is a systematic error in general that you have to add on top of that. And say the bad news are that your system is not your, let's say, your qubit is actually an open quantum system. And I don't want to go too much in detail here as well. I mean, I told you, I mean, we need to go quickly through many things. I mean, this would be probably deserve or start a new course, but there are mechanisms that essentially couple your qubit to the external environment, and that produce essentially two phenomena, mainly what is called decay and what is called dephasing. So the problem is that in general, in your system, if you prepare your system in what is an excited state, we said that when you call a state 0, 1, this doesn't necessarily, or actually almost never, coincides with the ground state of your machine. So when you prepare a quantum system in an excited state, this system actually is coupled to the external world and tends to decay. Okay, so suppose that you have a cavity which contains a certain number of photons, and the number of photons actually determines your state. These photons just get dispersed in a way, so that you decay from the state, and you try, and you go not to the ground state, you go to a thermal state. That's the problem. You're losing completely information, because what you will have in the end is not a system in the ground state, it's a system in a thermal state. Okay, so essentially you go towards a situation in which you remember the density matrix that we introduced. The density matrix gets to a matrix which has all the same elements. The elements are all equal to on the diagonal. Okay, so this means that you've completely lost any useful information. The phasing means that you can have instead via the coupling with the external world also the excitations into states that, or creation, for instance, of occupied states that are not part of the state, or I mean, have nothing to do with the state that you want to have in your machine. And so the problem is that you think your machine is at a certain state and instead it's not. So when I said earlier that when you perform a measurement, it's not trivial in general to decide, even if you have a two-state system 0, 1. You're not guaranteed that you will find your machine in a state that can be easily labeled 0 or 1 in general, because you could have the creation of mixtures. You could have, I mean, there are many mechanisms by which the physical system would be essentially destroyed, in the sense that the state is no longer what you think you have. And let me just mention one thing, just because this is an interesting, say, direction that one might think of in this field. There is an equation that typically you can use to describe these open quantum systems, and what is called the Lindblad equation. And in a form that it's applicable to a number of situations. This Lindblad equation contains some terms that describe this dissipation, and essentially, without these terms, this would be the unitary evolution of what we call the density matrix. We introduced the density matrix last time. And these operators D, let me erase, make some space. These operators D actually describe the dissipation in a very simplified way. So let's say that D of A and a dagger are the usual creation operation, creation and destruction operator, sorry, that act, for instance, on states that could be defined by, as I said before, the number of photons in a cavity or similar things, depending on the detail of the machine that you're using. So the action of this operator D on rho is something like A rho A minus 1/2 A dagger A, anti-commutator between A dagger A and rho, something like that. Okay. So you see, but besides the details, I mean, that don't tell you much probably right now, the important thing is that you have typically a couple of parameters, one that describe the decay one that describes typically the dephasing. That by which you can kind of reproduce the properties of a physical machine, so including these effects. And this is very important because when you set up an algorithm, you want to prepare yourself for running an algorithm on an actual machine. If you knew these parameters, you could sort of predict what is the systematic uncertainty, if you want, or the systematic deviations that you would see with respect to the ideal behavior of your algorithm. So you can also, for instance, test the robustness of an algorithm against this kind of phenomenon. So in general, people know that life right now is very limited in the quantum. This quantum world is very limited by these problems, and in general, we talk about the fact that we are living in the NISQ so-called era. What does it mean, NISQ? NISQ means noisy. So we are still coping with a number of problems in the engineering, if you want, of these quantum computers. And the noise actually is whatever goes and destroys the coherence of your state in the long run. IS means intermediate size, and this comes from the fact that the number of qubits that you have typically available in a machine, reliable qubits, is still quite limited, and Q stays for quantum. So you might hear, if you have a chance of listening to someone talking about quantum computation, this will probably pop out at a certain point, and people will say, here in the NISQ era, and the NISQ regime, well, not regime, this is really called the NISQ era, okay? So one refers to the fact that we are still in a situation in which the capabilities are limited in terms of noise and in terms of the size of the machines. Very quickly, because we are coming to the end. Oh, by the way, is there any questions so far? I think that I gave you, I just throw on you that a lot of information, but I don't know if there was any chance to absorb any of it, but if there are questions, so there is a question in the chat. Let's see. How do you approximate a unitary in practice? Yes, that's a good question. There are several ways. One way is that to construct, if you want to stick on this digital approach, you can construct some real compilers, in the sense that there are methods that allow you to express an arbitrary unitary in terms of a set of gates via some rules. Okay, these are a few rules. Okay, that allow you to express general operations, general matrices. Of course, the rules are such that what you get is not necessarily optimized, and how to optimize this process is a very active research field. So On one side, you can kind of automatically get the compositions. On the other hand, there is an approach I will tell you something about tomorrow, which is the one that kind of excited me first in this field. The fact that if you have access to the machine at a sufficiently low level, you can, in principle, create your own gates with very good approximation. So it's still in a way, I mean, this is kind of cheating, because in a way, you are also creating a set of gates. But these gates can be sort of created in a more analogic way. So it's like you have a quantum system. I will give more details tomorrow, but you have a quantum system. You send a pulse, for instance, or some external field in the system, and you just twist the system to the state you want, which actually means you apply some given unitary transformation that you want to apply, and you get the result you want in one single application of this gate. Of course, this means that you have to know beforehand what is the field, the character, what are the characteristics of the field that you have to send on the machine. So again, this costs as other costs. So it's a different problem, but in this NISC era, let's say, let's just use this term right away. This is still a reasonable approach. So you have essentially two alternatives. Either you use a set of predetermined gates and you compile your unitary transformation onto those, or you build your own gate for that specific transformation that you want, for the unitary you want in an analogic way. Okay. To tell the story very briefly, that I think, well, tomorrow I wanted to spend some time on that, because this is what the approach that we are having, and I will reserve some time for some commercials in that sense. So that's this will be included in the commercials. More questions? Hello. Okay. Hello. The way I understand the theorem is that the more gates, the better the precision and the approximation. The theorem gives clues about the speed of convergence. Yes. Is there an equivalent theorem on the classical side with bits and logic gates? Well, actually, logic gates. You mean by reconstructing an operation? An arbitrary operation on classical bits with gates, I guess. That's your question. And the answer is that, frankly, I don't know. So because I think there is something like that, but never went into that. This is a good question. I will check it out. Actually, thank you. This makes it's a very sensible question. More questions? Okay, otherwise, let me just show you quickly, but very quickly, a few things about the actual implementation of these machines. Yes, said thank you for the answer, but unfortunately I didn't answer, but that's as far as I can go with that. So let me share this one. I will just show you very quickly what are the principles actually. I have some slides, but I'm not going through all of them. I'll just browse them. So I just want, there are many practical implementations these days. There are three classes, if you want, three main classes of implementations. One is this one that we say something about, the circuit QED, so-called implementation. There is another one that generically makes use of cold atoms and lasers. So, for instance, you might have heard about so-called trapped ion machines that actually reproduce some Hamiltonians by manipulating atoms in different states and on optical within optical lattices. A third implementation is essentially based on photonics and on photonic devices that this also quite seems to be promising. Also because the first two typically have to work at very low temperature, while photonics might work even at room temperature, so that there may be some advantages with that. Quantum machines are things like that. I remember once in a movie seeing a scene in which the guys were looking for the quantum computer. They enter in a room. There is this nice picture of a thing like that, the skeleton, which is actually what stays inside a cryostat. So when you say a working quantum computer, you just say the cryostat and you see nothing else, because this is open, but of course in this form it's never going to work. Because things have to be run at more or less at the millikelvin level. There are some various implementations of the circuitry that goes in the refrigerator. This is, for instance, is a nice picture from Rigetti, which is a company that produces one of these machines. And you see these qubits, these small cavities here that are set at low temperature and that provide essentially the active component of the machine. What is this about? I mean, so the very general idea here is that, let's say, if you take a circuit, just an LC circuit, okay, you're supposed to put it, you put it at very low temperature, so everything is superconducting, so no resistance anywhere. This is really an ideal oscillator. And you assume that the size of the circuit is much smaller than say, the wavelength of associated to the frequency, the typical frequency of the system. Then you can sort of forget about the retardation effects, and you can describe your system in terms of a Lagrangian, in which essentially your degrees of freedom are the current that flows through the circuit, and the charge that you measure on the condenser. So of course you can transform this Lagrangian into an Hamiltonian. This is really like the Lagrangian of a classical oscillator. And once you have a Lagrangian of a classical oscillator, you can think that inside your cavity you have photons, if you want, and you can try to quantize the system. And so you can simply write down with a sort of minimal substitution, an Hamiltonian for an harmonic oscillator, in which essentially the current is given in terms of the flux to the circuit, and the charge is the charge, and you can construct a creation operation, creation and destruction. I don't know why today I keep saying that. Creation and destruction operators in this way. Okay, so somehow the idea is that if you take a circuit ideal oscillator at very low temperature, you can treat this as a quantum oscillator. If one wants to see some numbers, you can see that if you use frequencies of like 1,000 gigahertz or an impedances of about 100 ohms, you have that the energy associated is of the order of milli-electron volts, which is decent, is something that is not difficult to manage. On the other hand, you can also see that the fluctuations associated are of the order of fractions of the microelectron volt, and so vacuum fluctuations. So this is quite a stable system, and is an oscillator, is a quantum oscillator, which is usable in that sense. So the noise, the intrinsic noise doesn't destroy necessarily the state. It's quite stable. And these parameters are okay for existing electronics. So somehow the technical requirements are well within reach of what you can do these days. Okay. So why is an oscillator interesting? Because you can think of an oscillator as, if you want, a qubit in general. You could. Because you have, let me just draw here. You have your oscillator, you have your states, and you can fill up your states with photons. And actually, every time you throw in a photon, you change the state, and you can define a number of levels of your system, just counting the number of photons. Counting, I mean, doing spectroscopy at the single photon level on these devices is something you do these days. So this is not out of question. But there is a big problem if you just stop here. So this might be sort of a qubit, but it doesn't work as a qubit if I just count on the fact that I can fill the system with different number of photons, and I can so define a certain number of states of this cavity. What is the big problem? The big problem is that in a perfect harmonic oscillator, all these differences are the same, okay? These are all h bar omega, if omega is the frequency of the oscillator. So if I want to do spectroscopy of this thing, there are zillions of states that give me the same signal, just in the terms of differences of quanta. And this doesn't allow me to distinguish the state, to read out the state of the system. There is an interesting way of circumventing this problem, if you want. I should try to erase the stuff, otherwise it's okay. And the way of circumventing this problem is to couple the cavity to a nonlinear element. The favorite nonlinear element in general is a Josephson junction. And I'm not going to give you the theory of Josephson junctions because this is a little long in a way, but let me go down here. And typically you can reach, build up a circuit in which essentially the Hamiltonian that you can use to describe the system contains a term which is a cosine of the phase difference of the current at the sides of the junctions. You can think of a Josephson junction as a sort of permeable capacitor in some way. Okay, but the permeability is due to tunnel effect. Okay, and of course the density that you consider here, since we are in a regime in which the system is superconductive, should not be considered as the density of electrons, let's say, but rather the density of Cooper pairs. So there are a number of technical issues that theoretically also, but you can work out the theory. I mean, if someone is interested, they can give more details in another moment. But say at the end of the day, when you pair your ideal cavity to this nonlinear circuit, the miracle is that you have a system that has a spectrum that is no longer the spectrum of the harmonic oscillator, but it has levels that are well separated in energy, so that in such a way that you can actually do decent spectroscopy of the system, and you can go in and look at what is very reliably at what is the state of your cavity. So if you know how to count how many photons you have in here, you have a way to access many levels that will depend on the occupancy in terms of photons. Remember, the photons are bosons, so here you really have the possibility of creating many states because you do not have the constraints that you might think coming from occupying only once the level. So that's pretty nice. So say the average number of photons that you have in your system, sort of in each one of the levels, is something that you can use in order to give I mean, assign the state of the cavity. So in general, this is what you could call a QPU, a quantum processing unit. There are many ways in which you can realize this in practice. You can realize small circuits on a board. You can use actual cavities. I will show you one in a moment. But typically, the idea is that at the end of the day, you have an Hamiltonian that describes your QPU, this coupled system, which essentially contains terms that are related to the main frequency of the cavity, the frequencies of this nonlinear element, and then you have these couplings that actually are those that guarantee this separation of the level. On top of that, you can also, and we will discuss this tomorrow better. I mean, I will come back to this tomorrow. But just wanted to introduce a few things. You can actually couple the system with some time-dependent signal that can actually drive the signal one way, and it's also used to do the spectroscopy on the other way. Just to show you something, I mean, this is one of the cavities that we are using at Lawrence Livermore National Laboratory that make up the system with which we work, and we have worked recently. And you see, this is actually a a piece of metal which is carved, and there is this very clean carving that constitutes the cavity. You see these blobs here, these are the Josephson junctions that are in the cavity, so they are coupled to the cavity, and then you have some connectors to send in and out the signal. And things, you see that the dimensions of these cavities are a few centimeters, okay? So, and this means that one is working at frequencies that are the order of gigahertz. So these are all, I mean, the frequency of the gigahertz are very easily manageable. And say, this particular machine at the end of the day looks like that, okay? The refrigerator, this cavity is somewhere down here at the bottom of the refrigerator, then there is a lot of electronics going in, which is what allows you to communicate with the cavity and allows you to actually read the state of the computer. If you think of or remember the picture of the IBM machine, you see that this is more or less the same thing. You have the cavities down here that actually you will see. I mean, when you go in you will go in the website of the IBM Q, you'll see pictures of these cavities, and there are a lot of cables coming down. Of course, all this has to be put at a temperature of a few millik's. Tomorrow we'll say you something more about how to use these objects, in the sense that I will show you. I think I will say maybe I will say something about the variational quantum eigensolver method. That was the plan, but I might leave that for the end. On the other hand, I will show you how we attacked, or we are trying to attack realistic nuclear problems with this kind of machines. And what is the strategy that we're using, which is that of using the so-called optimal control, so that it's not necessarily projecting on gates. I will show you that these gates can be reproduced with a substantial fidelity, and I will show you some results. I will show you that what you can actually get in the solution, as I said, of realistic nuclear problem at large, in the sense that what you're doing is still limited in terms of number of nucleons, for instance. But it's interesting that you can already do problems of physical meaning.
E chi mi ha preso il mouse? Chi è che mi ha preso il mouse?
Okay, that's
Elena.
okay. That's external noise, but I think we're running out of time. I mean, I'm out of time already. So if there are questions. And if there are no other questions, I think we can adjourn to tomorrow.